Hello and thanks for watching. In this video I'm going to define the limit superior and the limit inferior of a sequence. Firstly I'm going to do it formally, and then I'm going to do it intuitively. I'm going to give a few examples, then give a harder example of where it may be used, and then give an exercise for the viewer to leave off. Okay, so firstly we define the limit superior of a sequence to be equal to the supremum of its subsequence after a certain value, and then we define the limit inferior of a sequence to be the infimum of the sequence of the subsequence after a certain value. Okay, so intuitively what this means is when we go to a really big term, then we're looking for the maximum value it can achieve, and then for the limit inferior, when we go to a really big term, we're looking for the smallest value it can achieve. Okay, so to head into some examples to make this clearer, if we have a sequence like this, then clearly we're just going between -1, then 1, then -1, then 1, and so on. Right, so when we get really big, this won't converge to any value. However, we know it's going to be either -1 or 1, so the limit inferior of the sequence is just equal to -1, because it's the smallest value our sequence can take when we get really big. And then the limit superior of our sequence is 1, because it's the largest value our sequence can take when you get really big. Okay, so moving on to an alternate example. If we take the sequence a half, and then 2/3, and then a third, and then 3/4, and then a quarter, and so on. Okay, we're trying to find the limit inferior and the limit superior of the sequence. So if we define a subsequence Bn, let's say, to be equal to a half, a third, a quarter, a fifth, and so on. So basically every odd term of the sequence. And if we define a subsequence to be 2/3, 3/4, 4/5, and so on, then we'll find the limit as both of these go to infinity in order to find the limit superior and the limit inferior. Okay, this is because this is just we know that this Bn is decreasing, and we know that this Cn is increasing. So the reason why we chose those to be our subsequences is because they're both monotone. And so we know that they're going to provide the limit inferior and the limit superior once we find the limit of them. Okay, so if we find the limit as n goes to infinity of bn, this is the same as finding the limit is n goes to infinity of 1 over n. Right, so this is just equal to 0. And so we may conclude that the limit inferior of our original sequence is just 0. And also we know that the limit as n goes to infinity of Cn is the same as the limit as n goes to infinity of n over n plus 1, which is equal to 1. This is because we can either compare directly and just say that this is the same as the limit infinity of 1 over 1 plus 1 over n, and this goes to 0, so it's 1 over 1. Or we can just think about it as n getting really, really large, so this 1 won't matter. So this is the same as having n over n really, and so we have 1. So the limit superior of an is equal to 1. Okay. So now to go on to a little bit of a harder example, I'll introduce a few things firstly, and then I'll solve a problem using solely the limit inferior and limit superior. Okay, so firstly, if we have the limit inferior of a sequence equal to the limit superior of a sequence, then we have that the limit inferior is equal to the limit superior, which is equal to the limit itself. And this is because, okay, so the limit inferior, informally, is the smallest value we can take when we get really, really big. And the limit superior is the largest value we can take when you go really, really big. So if the smallest value is equal to the largest value, we're really only looking at one value, which is the limit itself. Okay, and now I'll introduce an inequality based on the root test and the ratio test. So if we have the limit inferior, this is the of a sequence, sorry, of this is less than or equal to the limit inferior of this, which is less than or equal to the limit superior of this, which is less than or equal to the limit superior of this. Alright, okay. So I won't prove this. However, I will say that the limit inferior of a sequence is always less than or equal to the limit superior of a sequence, and intuitively that makes sense because we're really looking for the smallest and the largest value a sequence can take when we go really, really big. So it makes sense that the smallest value we can take is less than or equal to the largest value we can take, with equality being if the smallest and largest value are the same. So we're just looking at one value, i.e. the limit. Okay, so to use this now, let's say we want to find the limit as we go to infinity of this right here. This, I will say that this converges. You can use a test to check yourself, but this does converge. And the way you may approach this is by considering, okay, let's say from the above inequality, let's say an is equal to n factorial over n to the power of n. And the reason why we chose this is because, okay, if we take the nth root of this, we just get this. So this is our motivation for picking our an. So now if we want to calculate this is equal to n plus 1 factorial over over n plus 1 multiplied by n to the n over n factorial, which just gives us n to the n times n plus 1 over n plus 1 to the n plus 1. However, if we notice, these are the same, so we can cancel this out and this extra exponent, so we just get n to the n plus 1 to the n, which is equal to n over n plus 1 to the n, which is equal to 1 minus 1 over n plus 1 to the n, which is just, so when we take the limit as we go to infinity of this, we just get a 1 over e. So by using what we learned before, this, if these are equal, then they're also equal to the limit. So if we have a limit, then the limit inferior and the limit superior are also equal. So in this case, this limit inferior have 1 over e, okay, so we know that these middle two terms are bounded by 1 over e, but we don't have any values between 1 over e and 1 over e, so we know that both of these also must be 1 over e, and so they're also equal. So if we take the limit, so if we take the limit as n goes to infinity of n factorial to the power of 1 over n, this is between 1 over e and 1 over e, which means that the limit as n goes to infinity of n factorial over 1 over n is equal to 1 over e. And notice that we did not use any techniques to actually like evaluate this limit directly itself. We used bounding and then squeeze theorem, or squeeze theorem is just bounding a limit between two of the limits which are the same, meaning that the middle limit is also the same because it's got nowhere to go. Okay, so now to give an exercise for the viewer to leave off on, find the limit superior and inferior of this following sequence. Okay, thank you for watching. Hopefully limit superior and inferior makes some sense, and yes, bye bye.